This video is going to walk you through how to mark up the anchor text for the roller coaster unit. First off, find that anchor text in your Schoology account, and we are going to open that up in Notability. Let that load here. Create a new one. We'll import that. All right, and now we need to make a key so we know what we're looking for as we mark this up. Up here in the top, I'm going to make my key, and I'm going to use pink is going to represent anything that has to do with energy transfers. And I'm going to make anything green is going to be about energy conservation. I'm going to make blue is going to be about forces and those related effects. I'm just going to write the word forces here. And I'm going to add also a red highlight, and that will be any important vocab words. So with that, let's go ahead and start reading this article, keeping in mind what we want to highlight as we go through. So, how roller coasters work. Introduction to how roller coasters work. If you're studying physics, there are few more exhilarating classrooms than a roller coaster. Roller coasters are driven almost entirely by basic inertial, gravitational, and centripetal forces, all manipulated in the service of a great ride. Amusement parks keep upping the ante, building faster and more complex roller coasters, but the fundamental principles at work remain the same. Well, right there in that paragraph, it looks like we need to highlight some forces. So I'm going to pick my blue, and we're talking about the inertial, gravitational, and centripetal forces. In this article, we'll examine the principles that keep coaster cars flying around on their tracks. We'll also look at the hardware that keeps everything running, as well as the forces that make the ride so much fun. The amusement park industry has experienced a coaster boom of sorts in the past 15 years or so. New catapult launching techniques, hanging train designs, and other technological developments have opened up a world of options for designers. In recent years, designers have introduced coasters that have you lying flat against the train car so you feel as if you are flying, and coasters that shoot you down long stretches of spiraled track. Fourth dimension coasters spin or rotate your seat as the ride twists, turns, and free falls. In this article, we'll also keep you in the loop on all the newest features and innovation. So the rest of that page had a lot of interesting facts, but it doesn't look like anything fit under our categories, so let's go on to the next page. Roller coaster history. Roller coasters have a long, fascinating history. The direct ancestors of roller coasters were monumental ice slides, long, steep wooden slides covered in ice as high as 70 feet that were popular in Russia in the 16th and 17th centuries. Riders shot down the slope in sleds made out of wood or blocks of ice, crash landing in a sand pile. Coaster historians diverge on the exact evolution of these ice slides into actual rolling carts. The most widespread account is that a few entrepreneurial Frenchmen imported the ice slide idea to France. The warmer climate of France tended to melt the ice, so the French started building waxed slides instead, eventually adding wheels to the sleds. In 1817, the Russes et Belleville, Russian mountains of Belleville, became the first roller coaster where the train was attached to the track. In this case, the train axle fit into a carved groove. The French continued to expand on this idea, coming up with more complex tracks layouts, with multiple cars and all sorts of twists and turns. The first American roller coaster was the Mauch-Chunk Switchback Railway, built in the mountains of Pennsylvania in the mid-1800s. The track, originally built to send coal to a railway, was reconfigured as a scenic tour. For $1, tourists got a leisurely ride up to the top of the mountain, followed by a wild, bumpy ride back down. Over the next 30 years, these scenic rides continued to thrive and were joined by wooden roller coasters similar to the ones we know today. These coasters were the main attraction at popular amusement parks throughout the United States, such as Kennywood Park in Pennsylvania and Coney Island in New York. By the 1920s, roller coasters were in full swing, with some 2,000 rides in operation around the country. With the Great Depression and World War II, roller coaster production declined, but a second roller coaster boom in the 1970s and early 1980s revitalized the amusement park industry. This era introduced a slew of innovative tubular steel coasters. Some of the most popular ride variations, such as the curving corkscrew track, saw their heyday around this time. In the next section, we'll look at the coaster components that get the train rolling and bring it to a stop. All right, that section on roller coaster history had a lot of interesting facts, but again, it didn't seem to fit into our energy transfers or energy conservation or the forces, and it didn't really have much important vocabs. All right, let's go on. Roller coaster components. At first glance, a roller coaster is something like a passenger train. It consists of a series of connected cars that move on tracks. But unlike a passenger train, a roller coaster has no engine or power source of its own. For most of the ride, the train is moved by gravity and momentum. To build up this momentum, you need to get the train to the top of the first hill, the lift hill, or give it a powerful launch. Let's stop right there for a second. It looks like we're talking about some different forces here. So we're going to highlight that in blue. I think I'm going to start right here where it says for most of the ride. For most of the ride, the train is moved by gravity and momentum. To build this momentum up, you need to get the train to the top of the first hill, the lift hill, or give it a powerful launch. And you know, some of that looks like it's good vocab here, so I'm going to underline that in red. The lift hill and also the word momentum. All right, let's keep going. The chain lift. The traditional lifting mechanism is a long length of chain, or chains, running up the hill under the track. The chain is fastened in a loop, which is wound around a gear at the top of the hill and another one at the bottom of the hill. The gear at the bottom of the hill is turned by a simple motor. This turns the chain loop so that it continually moves up the hill like a long conveyor belt. The coaster cars grip onto the chain with several chain dogs, sturdy hinged hooks. When the train rolls to the bottom of the hill, the dogs catches onto the chain links. Once the chain dog is hooked, the chain simply pulls the train to the top of the hill. At the summit, the chain dog is released and the train starts its descent down the hill. Well, right there, it looks like we're talking about how energy is getting transferred. So I'm going to change my color to the pink. That was my energy transfer color. And I'm going to start marking up where it talks about once the chain dog, right here. Once the chain dog is hooked, the chain simply pulls the train to the top of the hill. And then it goes on to talk about at the summit, the chain dog, is released and the train starts its descent down the hill. So it sounds like energy is being transferred between that chain dog and the train itself. Let's keep going. In some newer coaster designs, a catapult launch sets the train in motion. There are several sorts of catapult launches, but they all basically do the same thing. Instead of dragging the train up a hill to build up potential energy, these systems start the train off by building up a good amount of kinetic energy in a short amount of time. Ooh, right there it's talking about some more of those energy transfers, so I'm going to continue highlighting in pink here. In some of the newer coasters, the catapult launch sets it in motion. They all basically do the same thing. Instead of dragging the train up a hill to build up that potential energy, These systems start the train off by building up a good amount of kinetic energy in a short amount of time. You know, it looks like we have a couple of good vocab words there too. The first one being this potential energy, and then also this kinetic energy. All right, let's keep going again. One popular catapult system is the linear induction motor. A linear induction motor uses electromagnets to build two magnetic fields, one on the track and one on the bottom of the train, that are attached to each other. The motor moves the magnetic field on the track, pulling the train along behind it at a high rate of speed. The main advantages of this system are its speed, efficiency, durability, precision, and controllability. Now, if we look at that, it looks like we're talking again about the forces and those related effects. So let's change that to blue. And I think I'm going to start right here when we talk about the linear induction motor, using those electromagnets. And I think I want to go through this whole next line. They're attracted to each other. The motor moves the magnetic field on the track, pulling the train along at a high rate of speed. All right. Another popular system uses dozens of rotating wheels to launch the train up the lift hill. The wheels are arranged in two adjacent rows along the track. The wheels grip the bottom or top of the train between them, pushing the train forward. The brakes. Like any train, a roller coaster needs a brake system so it can stop precisely at the end of the ride or in an emergency. In roller coasters, the brakes aren't built into the train itself. They're built into... Let's continue on to that next page. This system is very simple. A series of clamps is positioned at the end of the track and at a few other braking points. A central computer operates a hydraulic system that closes these clamps when the train needs to stop. The clamps close in on vertical metal fins running under the train, and this friction gradually slows the train down. It looks like there we're talking about some of the forces and some of the related effects. So let's go ahead and leave this as blue, and I'm going to start right here with a series of clamps, and they're positioned at the end of the track and a few at the other braking points. This hydraulic lift system that closes the clamps when the train needs to stop, and they close, and it causes friction that gradually slows the train. Now, I think there, a good important word that we need to focus on is that friction. So I'm going to underline that in that red. All right. Roller coaster physics. The purpose of the coaster's initial ascent is to build up a sort of reservoir of potential energy. The concept of potential energy, often referred to as energy of position, is very simple. As the coaster gets higher in the air, gravity can pull it down a greater distance. You experience this phenomenon all the time. Think about driving your car, riding your bike, or pulling your sled to the top of a big hill. The potential energy you build going up the hill can be released as kinetic energy, the energy of motion that takes you down the hill. Well, right there it looks like we have some good vocab words. So I'm going to zoom in here and I'm going to underline potential energy and kinetic energy. Potential energy, it says, is often referred to as energy of position. I'm going to go ahead and underline that so that we know what that definition is. And kinetic energy is the energy of motion. All right, let's continue. Once you start cruising down that first hill, gravity takes over and all the built-up potential energy changes to kinetic energy. Gravity applies a constant downward force on the cars. Looks like we have a couple different things going on in this one. So first off, I'm changing it to blue because it's talking about those forces and related effects. And I'm going to mark up gravity. It's that constant downward force. And then it also looks like we have some energy transfers. So I'm going to change to my pink here. And I'm going to start marking about the gravity takes over and that built up potential energy changes to kinetic energy. All right, now it has this picture here in the middle. This is from a website that you can go to and you can actually see this working, but we're going to continue reading the article. Click play to start the animation, which demonstrates how a roller coaster's energy is constantly changing between potential and kinetic energy. At the top of the first lift hill, there is maximum potential energy because the train is as high as it gets. As the train starts down the hill, this potential energy is converted into kinetic energy. The train speeds up. At the bottom of the hill, B, there is maximum kinetic energy and little potential energy. The kinetic energy propels the train up the second hill, C, building up the potential energy level. As the train enters the loop, D, it has a lot of kinetic energy and not much potential energy. The potential energy levels builds as the train speeds to the top of loop E, but it's soon converted back to kinetic energy as the train leaves the loop. Wow, that paragraph, it sounds like it is all about energy transfers. I am just going to make a little box around it instead of highlighting the whole thing. All right, let's continue. The coaster tracks serve to channel this force. They control the way the coaster cars fall. If the tracks slope down, gravity pulls the front of the car toward the ground, so it accelerates. If the tracks tilt up, gravity applies a downward force on the back of the coaster, so it decelerates. Since an object in motion tends to stay in motion, Newton's first law of motion, the coaster car will remain a forward velocity even when it's moving up the track, opposite the force of gravity. When the coaster ascends one of the smaller hills that follows the initial lift hill, its kinetic energy changes back to potential energy. In this way, the course of the track is constantly converting energy from kinetic to potential and back again. So it looks like here, this constantly converting energy is again about that energy transfer. So I want to mark up constantly converting energy from kinetic to potential and back again. This fluctuation in acceleration is what makes roller coasters so much fun. In most roller coasters, the hills decrease in height as you move along the track. This is necessary because the total energy reservoir built up in the lift hill is gradually lost to friction between the train and the track, as well as between the train and the air. When the train coasts to the end of the track, the energy reservoir is almost completely empty. At this point, the train either comes to a stop or is sent up the lift hill for another ride. Now, it looks like here we're talking about this total energy reservoir built up. That sounds like that's being how energy is conserved. So I'm going to switch to my green here, because the total energy is built up. It's gradually lost to friction between the train and the track, as well as the train and the air. All right. At its most basic level, this is all a roller coaster is, a machine that uses gravity and inertia to send a train along a winding track. Next, we'll look at the various sensations you feel during a roller coaster ride, what causes them, and why they're so enjoyable. Well, right there, it looks like we have a couple of vocab words. So let's take a minute and mark those. I'm going to mark inertia. All right. Roller coaster forces. In the last few sections, we looked at the forces and machinery that send roller coasters rocketing around elaborate courses. As you move over the hills, valleys, and loops of the track, the forces on you seem to change constantly, pulling you in all directions. But why is this rollicking movement so enjoyable, or for some people, so nauseating? To understand the sensations you feel in a roller coaster, let's look at the basic forces at work on your body. Whether you are on Earth, whenever you are on Earth, gravity is pulling you down toward the ground. But the force you actually notice isn't this downward pull, it's the upward pressure of the ground underneath you. The ground stops your descent to the center of the planet. It pushes up on your feet, which push up on your bones in your legs, which push up on your rib cage, and so on. Well, right there where it's talking about this whole Earth's gravity pulling you down, I think that that is actually about the forces and related effects. So we're going to change our color back to blue and mark that up. I'm going to start right here where it talks about Earth gravity pulling you down toward the ground, but you really notice that it's the upward pull of the ground underneath you. All right. At every point on a roller coaster ride, gravity is pulling you straight down. The other force acting on you is acceleration. I'm going to stop right there. We're just talking about another force. Force of acceleration. I think that's the first time we've talked about that word in this article, so I'm going to underline that as well in red. All right. When you are riding in a coaster car that is traveling at a constant speed, you only feel the downward force of gravity. But as the car speeds up or slows down, you feel pressed against your seat or the restraining bar. You feel this force because your inertia is separate from that of the coaster car. When you ride a roller coaster, all of the forces we've discussed are acting on your body in different ways. Newton's first law of motion states that an object in motion tends to stay in motion. That is, your body will keep going at the same speed in the same direction unless some other force acts on you to change that speed or direction. When the coaster speeds up, the seat in the cart pushes you forward, accelerating your motion. When the cart slows down, your body naturally wants to keep going at its original speed. The harness in front of you accelerates your body backward, slowing you down. All right there. This was talking about Newton's first law of motion, and that sounds like pretty good. Roller coasters and your body. Your body feels acceleration in a funny way. When a coaster car is speeding up, the actual force acting on you is the seat pushing your body forward. But because of your body's inertia, you feel a force in front of you pushing you into the seat. You always feel the push of acceleration coming from the opposite direction of the actual force accelerating you. That sounds like we are talking about those forces again. So we're going to change to blue. And I think I'm going to start right here where we talk about you always feel that push of the acceleration coming from the opposite direction, the actual force accelerating you. Okay. This force, for simplicity's sake, we'll call it the acceleration force. Ooh, good vocab word. Feels exactly the same as the force of gravity that pulls you toward the Earth. In fact, acceleration forces are measured in g-forces, where 1g is equal to the force of acceleration due to gravity near the Earth's surface, 9.8 meters per second squared, or 32 feet per second squared. So I think I'm going to mark that whole acceleration force and g-forces right here. No, I don't want to open in Safari. There. A roller coaster takes advantage of this similarity. It constantly changes its acceleration and its position to the ground, making the forces of gravity and acceleration interact in many interesting ways. When you plummet down a steep hill, gravity pulls you down, while the acceleration force seems to be pulling you up. At a certain rate of acceleration, these opposite forces balance each other out, making you feel a sensation of weightlessness, the same sensation a skydiver feels in a free fall. If the coaster accelerates downward fast enough, the upward acceleration force exceeds the downward force of gravity, making you feel like you're being pulled upward. If you're accelerating up a steep hill, the acceleration at the top of a hill in a conventional coaster, inertia may carry you up, while the coaster car has already started to follow the track down. Let go of the safety bar, and you'll actually lift up out of your seat for an instant. Coaster enthusiasts refer to this moment of free fall as airtime. I'm going to mark that airtime word because that is good vocab, I think. That sinking feeling. Airtime has a strange effect on your body because your body is not completely solid. It is composed of many loosely connected parts. When your body is accelerated, each part of your body is accelerated individually. The seat pushes on your back, the muscles in your back push on some organs, and those organs push on other organs. This is why you feel the ride with your whole body. Everything inside is being pushed around. Normally, all of the parts of your body are pushing on each other because of the constant force of gravity. But in the free fall state of plummeting down a hill, there is hardly any net force acting on you. In this case, the various pieces of your body are not pushing on each other as much. They are all essentially weightless, each falling individually inside your body. This is what gives you that unique sinking feeling in your stomach. Your stomach is suddenly very light because there is less force pushing on it. The same thing happens when you drive down a dip in the road in your car or descend in an elevator moving at a high speed. On a roller coaster, this full body sensation is complemented by all sorts of visual cues. The upside down turns, dizzying heights, and passing structures. Visual cues are an important part of the ride because they tell you that you are going fast. Your body can't feel velocity at all. It can only feel change in velocity, the acceleration. That is a good definition. So I am going to underline in red, starting here, that your body can't feel that velocity at all. It can only feel that change in velocity, which is acceleration. All right. The only reasons you know that you are moving quickly on a roller coaster is that the support structure is whipping past you at top speed and the air is rushing in your face. Roller coaster designers make sure to create plenty of tight fits and near misses to make you feel like you're rocketing through the structure at out-of-control speeds. One of the most exciting elements in modern coasters is the loop-the-loop. These structures turn the whole world upside down for a few seconds. Let's take loop-the-loops. As you go around a loop-the-loop, your inertia not only produces an exciting acceleration force, but it also keeps you in the seat when you're upside down. A roller coaster loop-the-loop is a sort of centrifuge, just like a merry-go-round. In a merry-go-round, the spinning platform pushes you out in a straight line away from the platform. The constraining bar at the edge of the merry-go-round stops you from following this path. It is constantly accelerating toward the center of the platform. Well, right there, I think I'm going to underline this word centrifuge because that's a pretty good one. The loop-the-loop in a roller coaster acts exactly the same way as a merry-go-round. As you approach the loop, your inertial velocity is straight ahead of you. But the track keeps the coaster car, and therefore your body, from traveling along this straight path. The force of your acceleration pushes you from the coaster car floor, and your inertia pushes you into the car floor. Your own outward inertia creates a sort of false gravity that stays fixed at the bottom of the car even when you're upside down. You need a safety harness for security, But in most loop-the-loops, you would stay in the car whether you had a harness or not. I think that inertial velocity, I'm going to mark that as a good word too. Okay. As you move around the loop, the net force acting on your body is constantly changing. At the very bottom of the loop, the acceleration force is pushing you down in the same direction as gravity. Since both forces push you in the same direction, you feel especially heavy at this point. As you move straight up the loop, gravity is pulling you into your seat, while the acceleration force is pushing you into the floor. You feel the gravity pulling you into your seat, but if your eyes are still open, you can see that the ground is no longer where it should be. Ooh, right there, we're talking about that net force on your body. That to me sounds like some forces and related effects. And we're doing that in blue. So I'm going to start right here with the net forces, that those net forces are constantly changing. All right. At the top of the loop, when you're completely upside down, gravity is pulling you out of your seat toward the ground, but the stronger acceleration force is pushing you into your seat toward the sky. Since the two forces pushing you in opposite directions are nearly equal, your body feels very light. As in the sharp descent, you are almost weightless for the brief moment when you are at the top of the loop. As you come out of the loop and level out, you become heavy again. The loop is amazing because it crams so much into such a short length of track. The varying forces put on your body through the whole range of sensations in a matter of seconds. While these forces are shaking up all the parts of your body, your eyes see the entire world flip upside down. To many coaster riders, this moment at the top of the loop, when you're light as a feather and all you can see is the sky, is the best part of the ride. In the loop, the intensity of the acceleration force is determined by two factors, the speed of the train and the angle of the turn. As the train enters the loop, it has maximum kinetic energy. That is, it's moving, sorry, I need to zoom out here. It's moving at top speed. At the top of the loop, gravity has slowed the train down somewhat, so it has more potential energy and less kinetic energy. It's moving. Now, the beginning of this part kind of sounds like it's about forces and those related effects on your body. So I'm going to mark that here in blue. I'm going to start in the loop. The intensity of the acceleration force is determined by the two factors, the speed of the train and the angle of that turn. All right, let's keep going here. Originally, roller coaster designers made circle-shaped loops. In this design, the angle of the turn is constant all the way around. In order to build an acceleration force strong enough to push the train into the track at the top of the loop, they had to send the train into the loop at a fairly high rate of speed, so it would still be going pretty fast at the top of the loop. Greater speed meant a much greater force on the rider as he entered the loop, which could be fairly uncomfortable. The teardrop design makes it much easier to balance these forces. The turn is much sharper at the very top of the loop than it is along the sides. This way, you can send the train through the loop fast enough that it has an adequate acceleration force at the top of the loop, while the teardrop shape creates a reduced acceleration force along the sides. This gives you the force you need to keep everything running without applying too much force. All right, this part here seemed to talk about how energy is being transferred. We were doing that in pink, so I'm going to switch to my pink. And I think I'm just going to make a box along here that again just shows that that whole area is kind of talking about how that energy is being transferred. And let's continue on to these types of roller coasters down here. There are two major types of roller coasters, distinguished mainly by their track structure. The tracks of wooden roller coasters are something like traditional railroad tracks. In most coasters, the car wheels have the same flange design as the wheels of a train. The inner part of the wheel has a wide lip that keeps the car from rolling off the side of the track. The car also has another set of wheels, or sometimes just a safety bar, that runs underneath the track. This keeps the cars from flying up into the air. Wooden coaster tracks are braced by wooden cross ties and diagonal support beams. The entire track structure rests on an intricate lattice of wooden or steel beams, just like the beam framework that supports a house or skyscraper. They can even flip the train upside down, though this is rare in modern wooden coasters. But because the track and support structures are so cumbersome, a wooden track is fairly inflexible. This makes it difficult to construct complex twists and turns. In wooden coasters, the exhilarating motion is mainly up and down. The range of motion is greatly expanded in steel roller coasters. The world of roller coasters changed radically with the introduction of tubular steel tracks in the 1950s. As the name suggests, these tracks consist of a pair of long steel tubes. These tubes are supported by a sturdy, lightweight superstructure made out of slightly larger steel tubes or beams. Tubular steel coaster wheels are typically made from polyurethane or nylon. In addition to the traditional wheels that sit right on top of the steel track, the cars have wheels that run along the bottom of the tube and wheels that run along the sides. This design keeps the cars securely anchored to the track, which is absolutely essential when the train runs through the coaster's twists and turns. So, that's telling us a lot about roller coasters and how they're built, but it doesn't talk about the energy transfers or energy conservation or, the forces and related effects very much. So I think I'm going to keep reading here. The train cars and tubular steel coasters may rest on top of the track, like the wheels in a traditional wooden coaster, or they may attach to the track at the top of the car, like in a ski lift. In suspended coasters, the hanging trains swing from a pivoted joint, adding an additional side-to-side motion. In an inverted coaster, the hanging train is rigidly attached to the track, which gives the designer more precise control over how the cars move. A tubular steel track is a prefabricated in large, curved segments. The steel manufacturing process allows for a smoothly curving track that tilts the coaster train in all directions. A wooden roller coaster rattles as it rolls over the joints that connect the pieces of the wooden track. In a tubular steel coaster, the track pieces are perfectly welded together, making for an incredibly smooth ride. As any coaster enthusiast will tell you, each sensation has its own distinctive charm. According to the Roller Coaster Database, there were 2,088 coasters in operation around the world in 2007, 1,921 of them steel, 167 wooden. The RCDB identifies 8 main coaster types: sit down, stand up, inverted, suspended, pipeline, the track is attached to the middle of the train instead of above or below it, bobsled, wheeled trains slide down a U-shaped tube instead of being fixed to a track, flying, riders start out in a seated position but are rotated to face the ground as the ride starts, giving the feeling of flying. Fourth dimension, 2 seats from each car are positioned on either side of the track. The seats spin or rotate on their own axis, either freely or in a controlled motion. In 2007, there were only 4 fourth dimension coasters in operation. You know what? All of those seem to be really good kind of vocab-y words. I don't know so much if they're going to help me understand how energy is being transferred, but I think I'm just going to make a red bracket mark around these. Just if I want to reference those. Never been on a coaster before? In the next section, we'll give you some advice for your first ride. Safety tips for a first-timer. So, you're finally taking the plunge. For years, you've been playing it safe on the bumper cars and kiddie rides, but now you're ready to try the real deal, a coaster. Once you're in line, though, the blood-curdling screams coming from the ride could make you think you're about to put your life at risk. You might want to turn around and head back to the carousel. But really, how dangerous are roller coasters? First of all, it's important to know that the numbers are on your side. According to the International Association of Amusement Parks and Attractions, 335 million people visited U.S. theme parks in 2006, source IAAPA. A study that year by the Consumer Product Safety Commission found that around 6,500 people seek medical attention every year for injuries at theme parks. This includes non-ride injuries. Of that number, about 130 required overnight hospitalization, making your risk of serious injury just from stepping into the park about 1 in 25 million. The chance of a fatal injury at a theme park is 1 in 1.5 billion. Source, CPSC. By comparison, the chance of fatal injury in a car crash is almost 15 in 10,000. Source, the U.S. Department of Transportation. In 2003, the Brain Injury Institute of America released a study that concluded in part that the risk of brain injury from a roller coaster is not in the rides, but in the rider. Source, Brain Injury Institute of America. Of the 6 fatal injuries the study examined, all had been caused by previously undetected brain conditions. Basically, use common sense. If you have or think you might have any of the conditions posted on the warning signs, i.e. high blood pressure, heart disease, or heart condition, pregnancy, don't get on the ride. If you've been consuming alcohol or if you don't meet the height and weight requirements, you are putting yourself at risk by riding a roller coaster. Once you've made it into the coaster car, you'll be secured by one of 2 basic restraint systems, a lap bar or some variation of an over-the-shoulder harness. Don't be alarmed if you're getting on the loop-the-loop coaster with a lap bar. As we saw earlier, inertia would keep you in your seat even with no restraints. The restraint system and everything else on a roller coaster is completely computer controlled. Programmable logic controllers, usually 3 of them, monitor every aspect of a coaster's operations. They regulate the rider's speed, ensure that the trains never come too close to one another, and alert human operators to technical glitches or track obstructions. There is no possibility that, say, the ride would leave the station with an unsecured safety belt, or that an attendant would forget to apply the coaster's brake. All coasters are carefully inspected on a daily basis and completely worked over during the park's off-season. Even armed with these facts, you'll probably still be a little nervous. Just remember that roller coasters are designed to give you a thrill, to make you feel like you're in danger, if only for a few seconds. So just sit back, relax, and enjoy the ride. For much more information on roller coasters and related topics, check out the links on the next page. All right, that looks like everything. Again, just a reminder, if we go back to that very beginning, the things that we were focusing on were energy transfers, energy conservation, forces and those related effects, and vocab words.